Hello and welcome to 70th lecture in 19th chapter of our comprehensive course on AI, ML and DS. Now here we want to talk about the key assumptions of central limit theorem, that is under which conditions you can use central limit theorem. So first assumption is independent sampling. Now that we had seen that the whole this thing black colored, that is the population, say the data of Walmart customers of 100 countries, and that is 2 million rows are there. Now from which I am drawing these samples shown by blue, yellow, orange, red, pink, etc. colors. Then each sample must be independent of each other. So that means not only sample, but in the sample also each data point must be independent of each other. Okay, so the sample data point must be independent of each other. Now that is called an independence assumption, and in real world scenario sometimes this independence does not hold, and there are ways to check it whether it holds or not. So sometimes what happens is the data points are correlated with each other. There is some correlation between various data points of one sample, or sometimes even one sample and another sample also. Then in that case, you cannot say that they are fully independent. But even in such case, you have to see to what degree they are correlating. If the correlation is mild, okay, that means if the independence is not full but mildly dependent points are there in a sample, still you can use central limit theorem, because the error which that introduces is not that significant compared to not having any tool. It is better to have some tool which gives at least say 98% accurate answer compared to the not using central limit theorem, right? One more thing is about sample size. Now here I used to use that word if there are sufficiently large number of samples. Now sufficiently large number of samples means usually as large as possible, but minimum around 50 samples are required. But that can be taken care by some special tricks. What are those tricks that are coming just now? So sometimes it is possible that the population is not very big, and therefore you can draw only say maybe 50 samples. But suppose for central limit theorem, at least 100 samples were required. Okay, then you can do some tricks, and still out of 50 samples also you can take the work of 100 samples. That is possible by certain tricks. So that means the number of samples is not much a limiting factor for using central limit theorem. But the number of data points inside each of these samples, that is one important factor. So each sample should be sufficiently large. However, fortunately sufficiently large does not require some hundreds of thousands of data points inside each sample. You just require greater than 30 data points for any sample inside each sample. The number of data points should be greater than 30 for central limit theorem to hold. And third and the most important condition for central limit theorem to hold is that the population which is being sampled must have finite mean, mu, and finite variance. So I told you that the original population may be normal, maybe uniform distribution, maybe exponential distribution, or maybe any other distribution out of all those data distributions which we had seen, right? But any distribution is allowed, but there are certain distributions among all these, they have infinite mean, and those kinds of distribution are not allowed. For example, one of that kind of distribution is this C.L.T distribution. Now there the mean is not finite and standard deviation is also not finite. So if it is that kind of situation, then central limit theorem does not hold. So if my population follows C.L.T distribution, then in that case I will say that central limit theorem will not be usable, right? So what are three conditions? One, samples must be independent of each other, okay, and there should not be any much of each data point within the sample also must be independent of each other, okay, and there must not be even mild dependence or correlation. Sample size, that is the number of data points inside each sample, should be greater than or equal to 30 at least, and the original distribution can be any distribution except a distribution like C.L.T distribution or some that kind of distributions where the mean and standard deviation are infinite. So original population can have any distribution, that is fine, but one condition is there, that its mean and standard deviation should be finite. So some heavy tail distributions are there which do not obey that condition, so you cannot use central limit theorem. Now one more question which may arise is, okay, central limit theorem says that whatever is the distribution of original population, may it be normal, may it be uniform, may it be exponential, etc., But if I take sufficiently large number of samples, say 50 to 100 samples, and or more than that, more is always better, right? And in each sample there are 30 or more observations, and these three conditions are obeyed, then in that case, the means of the sample, they are always normally distributed. That is what central limit theorem guarantees. Now, one question which may arise in our mind is, what is the need to be so gung ho about that whole thing? That okay, the means are normally distributed, but why? What is the importance of that thing? Now, this normality of means is the key assumption in many data analytics technique. So, central limit theorem assumes that even if the raw data is not normal, whatever is the distribution of your raw data, these three or black colored or any other distribution, the sampling distribution of mean will always be normal. This blue color sampling distribution of mean will always be normal. This allows us to do parametric tests like t-tests and ANOVA. What are these tests we are going to see later on in the statistic portion. So, but parametric tests are always considered much more robust compared to non-parametric tests. What are non-parametric tests? That also we will see. But why these parametric tests are so robust and reliable? That is because they are based on central limit theorem. So if central limit theorem would not hold true, then the parametric test would not be so reliable. Then they allow us to conduct the confidence interval for metrics like mean or accuracy or loss. Now that is also important, because what you do is, actually we often go on speaking that kind of word that my machine learning model is having accuracy of 89%. But what is the meaning? If you see the whole process, you start with a population, then from a population you draw certain number of samples, say 50 to 100 samples, and each sample should have minimum around 30 or more data points, right? So these are various samples. Then you find the accuracy for these sample by dividing it into train test, dividing these also train test, divide these also in train test, divide these also, then train the model on the training data set and find the accuracy. So you will get one value of accuracy for these, one value of accuracy for these, one value of accuracy for this, one value of accuracy for this. So when you say that my model has accuracy 89%, that is actually the mean accuracy which you have got on all the samples. Okay. So that is the mean of accuracy which you have got on all the samples. Of course, the algorithm automatically takes care of this thing, taking several samples, finding accuracy for each sample, and then taking mean of it. It just displays the result that the accuracy is 89%. So we often forget the underlying mechanism, but the underlying mechanism is like this, that what you are getting is accuracy of mean accuracy or mean loss. We often say accuracy is 11%, or we say that the loss is accuracy is 89% or say loss is 11%. Another way of speaking the same thing, right? But before which this mean word is not even spoken many times. So learners often forget that internally the algorithm does this, that from population it takes several samples, it finds the accuracy for each sample, and whatever number it displays finally, that accuracy is 89%. That is the mean accuracy for all the samples, right? And there also mean accuracy for all the samples, we write it with some confidence interval, like say 89% is fine. But as I have often told you, that for most application we write 89% or 0.89 plus or minus 0.05, or if you write in percentage, then in that case you will write that 89% can be written this way, that 89% plus or minus 5%. So that means the actual accuracy of model can be 84% to 94%, right? So it can be 84% to 94%. So then that is called, this is called confidence interval. That in this much interval, I am confident that my accuracy will fall between 84 to 94. It will never be less than 84, or it will never be greater than 94 also. But why we can write such confidence intervals and everything, that is also thanks to central limit theorem. And last and the most important thing is, we can make probabilistic predictions about future outcome, particularly in classification. Suppose you are asked whether this customer will churn or not, then you decide one threshold of probability, that the probability threshold is equal to, say for simplicity I write 0.5 or 50%. Now if I find my probability of churning, yes or no, for say 3 customers, this is customer 1, customer 2, customer 3, and the probability that I am getting for these 3 customers are, suppose for these customers I get 0.6, for these customers I get 0.45, and for this customer I get 0.55. So that means, then I will say that wherever the probability is more than my threshold of 50% or 0.5, I will say that here probability is 60%. So I will predict that yes, this customer is likely to churn, but here it is only 0.45. So then I will say that no, this customer is not likely to churn. And I will here also say that this is 0.55. So yes, that is, he is likely to churn. Okay. Now you will be surprised, but in machine learning and even in other, for example, recent this ChatGPT and all these, they are all probabilistic models. They do not give answer in categorical manner like this, yes, no. They just give some probability, and depending upon a threshold and a lot of fine tuning, you can get the answer in this manner. Okay, so but again, that is possible. Making such probabilistic predictions is possible. That is because of central limit theorem. Because probability will work provided the statistical facts about population and the statistical facts about samples are same. Okay, so you can never study the whole population as completely, because it is always too large. But you want to draw the conclusions, probabilities for the entire population. So you are studying a sample or more than one sample, say 550 to 100 samples, that is another matter. But you are taking at a time one sample and find probability for various points of that sample. But why that probability is applicable when that sample is in presence of all other samples and all those things? Okay, that means why that probability which you are finding for a sample is applicable when those data points are actually part of one whole large population. That is thanks to central limit theorem. Okay, so central limit theorem, this normal assumption, not assumption, sorry, the normality of the mean, which central limit theorem guarantees, irrespective of the distribution of original population, that is the basis of three things. It allows us to use parametric tests, it allows us to construct confidence interval, and it allows us to make probabilistic prediction, right? So now you understand, and you will be surprised, but this is more than 60% of the data science. Okay, so that means that central limit theorem is called, its name itself is central. Okay, so central means it is the heart of data science, central limit theorem. Okay, however, it also has certain limitations. Now that limitations can be easily remembered from these assumptions only. If these assumptions are not satisfied, then you cannot use the central limit theorem. So that becomes the limitation. Okay, for example, here we say that sample size should be at least 30 or more. So if sample size is too small, for example, sample size is just 5, then in that case you cannot use the central limit theorem. Here we try to plot for a sample size of 5, then we got an extremely skewed distribution. Our original distribution was also skewed exponential, and this is not exponential, but at least this part you can see that is looking like exponential only. So for sample size of 5, you cannot use. So small sample, then central limit theorem is not applicable. Heavy tailed distributions, for example, Cauchy distribution, then central limit theorem is not applicable, because there the assumption that the original population must have some finite mean and some finite variance, that assumption is not obeyed, right? And dependent sample, if samples are dependent, as I said, if they are mildly dependent, we take it, okay, we will use it, central limit theorem. But if there is heavy interdependence between data points in the sample, so in that case you will not be able to use central limit theorem, and that means you will not be able to use this t-test ANOVA, you will not be able to construct confidence interval, and you will not be able to calculate probabilistic predictions. When I say you will not be able to do, you can do, that is fine, but they will no longer be sufficiently accurate. Okay, if the samples are dependent and the data points are dependent on each other, then in that case this will no longer be applicable, right? Now here, this one very important example is that time series data. Time series data is a very simple example is the for example the stock market data. Now here suppose on this axis the date is plotted, and on this axis the price of a particular stock is plotted. Then we all know that the price of a stock varies in this manner. Okay, this way. This kind of graph, that is called time series. It's not always necessary that it would go on going up only, but let's just a little bit feel good. So then this kind of graph is called time series. Now the problem with time series is that it's independent observation. It's each observation that we say this is one data point, this is another data point, this is another data point. Data point means price at that point, and this is the date and time at that point. This is the date and time at this point. On x-axis date time is there, and on y-axis the price is there. Okay, so if I plot this kind of plots, and then I draw a graph passing through all these blue crosses, then that graph is itself called the time series, which displays me which represents the variation in the stock price, right? Now the problem with this is that whenever this time series is simplified for analysis, then it is found that the value of each data point is not independent, but the value of each data point depends strongly on this previous data point. So that means today's price of stock seems to be strongly dependent on previous day's price of stock. Then it seems to be slightly weakly compared to this. So here suppose the dependence is say 90%. Then if I take still one more day's price, then this today's price and 2 days back's price, they depend on each other, say 80%. Numbers I am just writing as an example, so don't much go by number. But the point is, as I take my past date further and further away from today, then the dependence goes on decreasing. Here also, suppose this is 10 days back price, So then the dependence of today's price on that 10 days back price is 20%. But it does depend, and that violates the basic condition of central limit theorem, right? That data point must be independent of each other. So that is why time series analysis cannot be done by using normal statistical techniques. So we have kept a whole chapter on time series, but you will see that for time series we don't do all those things like hypothesis making and all those things. We just convert the time series we just use totally different techniques. A different technique, basically, in one sentence if I tell you, then this time series is divided into three. It is called differentiating the time series. Differentiating means instead of this graph, same graph is represented by three different graphs. One is called trend. So here the trend is going upwards, so it is a straight line. This is the trend because the stock price is going upwards. It is not necessary that it is always going upwards, okay? That is, if the graph is like this, then the trend would be downwards. One is the seasonality. Now, seasonality is if this is, say, stock of some automobile sales, then you see that automobile sales do not just go on keeping upwards. In festival season like Diwali or Dashera or maybe other that kind of days which are considered auspicious, on that days the sales suddenly jump, but thereafter the sale go down. So that means actually the graph is somewhat this kind, okay? Seasonal graph. Okay, so this is called a seasonal graph. There are periodic peaks and troughs, okay? And the third component of this time series is this kind of auto-regressive or noise, okay? So every time series can be broken into these parts. But in short, this whole analysis is not at all done by this t-test and ANOVA and or it is not even done by that dividing the data set into train and test and all those things, right? So this is a totally different thing, and therefore you cannot use central limit theorem and you cannot use these methods for it, right? Okay, so dependent samples like time series, they cannot be handled using central limit theorem. Now then the question which may arise is that so then is that the end of central limit theorem? That means that suppose some conditions are not satisfied. See, we now know that central limit theorem will not work if sample size is at least should be at least greater than 30. So for this kind of sample size it will not work. So is that the end of central limit theorem? No. There are some other extensions of central limit theorem given. For example, this is one statistician's name and he has given an extended version which relaxes the assumption of identical distribution. Now this is very important because when we take samples from the population, there are two assumptions. One is the independence. When we take this kind of samples from the population, one assumption is independence, that each sample is independent of each other, and another assumption is that samples are identical in all other ways. So that means if this is a sample of around 30 data points, this cannot be a sample of 500 data points, then this can be a sample of again 5 data points, then this can be a sample of 10,000 data points. Even if you have 2 million data points, if one is a sample of say 100 data points, then all others also should be more or less same, right? So that is the meaning that the samples should be independent of each other and they should have identical distribution. But then that is a condition for central limit theorem. But this extension of central limit theorem given by Lyapunov, that says that this identical distribution will, even if it is not applied, okay, then it is fine, okay, and it does apply to independent but not identically distributed random variables, okay, provided certain conditions on variance and higher moments are met. So that means that even if the samples are not identically distributed, but as long as they are independent, the first and the important condition is satisfied, you can use this extended version of central limit theorem. Similarly, there is another Lindbergh-Feller central limit theorem that can be used for a sequence of random variables where no single variable dominates the sum. So even highly diverse data can yield normal sampling distribution under specific condition. The data may be totally diverse from each other. So here that independence is there, but now even suppose again you are not having identical distribution, but still if totally diverse data is there, then central limit theorem in its original form does not work, but these two statisticians have given its another extended version. And one is multivariate central limit theorem that is applicable for random vectors. Vector is one particular row of a data set. Say suppose you have an Excel sheet like data frame this way, correct? And here this is my first feature, feature 1, this is my second feature, feature 2, and so on up to these are my other features, feature n, and this is the response variable which I am trying to predict. Okay, so now this is my first row of data, this is my second row of data, This is my third row of data. And similarly, there are such 10,000 rows like Excel sheets. Okay. Now I think you are understanding. These are columns, which I call features. They are columns, and each observation or each record is a data. Is called a vector. Okay. Then for random vectors, this central limit theorem does not work. It works only if these various of course, first row and second row will contain different values, but they should not be completely randomly different. But even in that case, this multivariate central limit theorem can be applied. Okay, so there is one thing, and this is real life example of application of central limit theorem. Suppose a business collects monthly data of customer retention across different regions. So suppose my business is spread over all the states of India and in four main regions: north, east, south, and west. So I am collecting customers' data from these four regions. Now, what is the problem with that? Then each region's data may or may not be following normal distribution. In fact, most of the time, each region's data will surely not be following normal distribution. Why? Because each region has some of its local characteristics. So that means expecting this kind of data from the population, northern population, western population, eastern population, or southern population, no population out of four will have this kind of data. Okay, normally distributed. Why? Because each local market has certain local characteristics which will distort or skew the distribution in one or other direction. Right? Now, then what we do? How do we still get a company? Whenever you have seen companies' annual reports or something in the stock market listed companies, so a company just say that next year we are expected to make 8% growth in our revenue and 15% growth in our this uh, profit after tax. They don't say that in north region we do this much and in west region we'll do this much and in east region we'll do this much. They just give an aggregated number. So why? Because they use central limit theorem and they find customer retention, aggregate customer retention across all regions, and then calculate the mean retention rate and then construct the confidence interval. But what is the basis of such aggregation is allowed for such diverse data, diverse populations? Because I said that northern, eastern, western, and southern population of customers, they have totally different characteristics due to the local factors. So central limit theorem guarantees that even if you do aggregation over all regions and find the mean retention rate, and then the mean retention rate would be following the normal distribution, and we can easily conduct confidence intervals like these for various metrics on it. Okay, so this is the real life example: customer retention by a large pan-Indian company in north, east, south, and west four regions. Okay, next lecture we want to do about this thing. Okay, that is beauty of central limit theorem, key takeaways from central limit theorem, practical applications, and then we will try to do more understanding by actual plotting also, so that we can get some idea about central limit theorem. Okay, so that will be next lecture. So bye for now.